Good morning all. So today we are going to discuss about the demodulation for DSB-SC signal. Now last class we have discussed about the modulators. Okay. So we have seen the two modulators as well as we have discussed about the spectrum analysis. We have discussed about the mathematical relations, as well as we have discussed about the power calculation for generation of DSB-SC signal with respect to balance modulator and with respect to ring modulator. Now ring modulator is quite similar to the switching modulator, okay, that we have seen. As your diode in our switching modulator to generate an AM signal, first we are generating the DSB-SC signal and then we are adding the carrier component to it so that AM signal is generated. But the thing is, in order to generate the positive half as well as for negative half, we require a full wave bridge rectifier. So full wave bridge rectifier, as in the ring modulator you see that 4 diodes are used. 2 diodes are used for the negative half cycle and 2 diodes is used for positive half cycle, so that continuous wave it will get. So output of that particular modulator is the continuous signal what we have seen in our diagrams as well as analysis part. But in that case only the sideband with modulating signal is available, but carrier component is suppressed. Now once those signals are transmitted, next what we have to do? We have to detect. So how many type of detector we have discussed? We have discussed synchronous detection, or it is also called as coherent detection. Second, envelope detection. Third, square law demodulator also we have seen for AM signal, as well as squaring loop detection is also identified. So for the detection of DSB-SC signal, we will discuss the 3 demodulators. Then we will go for the if I want to transmit the 2 DSB-SC signal in a common channel, what is the type of modulation I will do, that we will discuss in this particular class. Okay. So one by one we will start. So today we will discuss about the demodulation of DSB-SC signal. Okay. So as the word demodulation means, we need to extract the original message component from the received modulated signal. So how we can extract, that process is called as a demodulation. Okay. So now first we will discuss about synchronous detection. Okay. This is the first one we will discuss. This is a very simple one. Then second we will discuss about envelope detector. Okay. It is also quite interesting one. And third we will discuss about squaring loop detector. Okay. So these detectors are basically used to demodulate your DSB-SC signal. Now how we can analyze these signals? Okay. So what I will do, first I will analyze the transmitter part and then I will analyze the receiver part. So in transmitter part what happens, message component is provided to the product modulator, or you can say it is called balance modulator. Okay. So it is a product modulator in which the carrier component is provided, that is cos omega Ct, and this is m of t, and you will get the DSB-SC signal. And this carrier is generated with the help of local oscillator. So here we have generated the DSB-SC signal. So this is the basic block diagram to generate the receiver part what happens? So here it is transmitted. So at the receiver part what happens? Again, in order to demodulate, we need to synchronize the same carrier frequency, okay, with same strength or may not be the same strength, but the frequency or the phase must be synchronized. Then only it will come under our synchronous detection. So here I am providing the cos omega ct, and here I am receiving the DSB-SC signal in which it is processed through the product modulator, okay, product modulator, or you can say it is a mixer, no problem. Then output must be passed through the low pass filter, and this output must be our modulating signal. So this is the basic concept of our synchronous detection. So here I will write synchronous, okay. So this is the synchronous detection. So in this detection, I am generating the DSB-SC signal, extracting the modulating signal if I am receiving the DSB-SC signal here, okay. So this is my DSB-SC signal I am receiving. From the help of local oscillator, carrier frequency is provided, and we are receiving some sort of signal to the low pass filter, and the low pass filter will only pass the modulating frequency, because at the center frequency to the FM, that is modulating frequency, and the higher component are suppressed, okay. So this is the basic logic behind your synchronous detection. Now this logic we need to express with the help of mathematical analysis. Okay, then we will analyze the frequency spectrum. So step by step we will see. So here I need to generate the DSB-SC signal. So DSB-SC signal, S suffix DSB-SC of t, I can write C of t into M of t. Done. Now this C of t is nothing but the cos omega ct. So directly the amplitude of a carrier is going to be changed with respect to the modulating signal. So this is my DSB-SC signal. Okay. Now once this DSB-SC signal is generated, it is transmitted over a particular channel and it is received toward a receiver end. So at receiver end what happens? This is transmitter part, generation of DSB-SC signal. Then at receiver end what happens? We receive the DSB-SC signal modulated. This product modulator act as a mixer over here, in which cos omega ct is multiplied with the received modulated signal, and then we are getting some output. Let us consider this is D of t. Okay. Now here I can say the output of mixer, that is D of t, that is S of t into C of t. Done. Now here we have synchronized it. We have also discussed if there is a phase difference what will happen. Okay. So we will discuss that also. So first S of t is multiplied with the carrier. We will get M of t cos square omega ct. So this is the D of t. Now this D of t need to be expanded so that harmonic component can be known. One component will be M of t by 2, one component will be M of t cos 2 omega ct whole divided by 2. Now here you can see that this particular part, it is a sideband, no matter, it is a sideband having upper sideband and lower sideband, but it is for second harmonic frequency, which is the higher frequency, which will be suppressed by the low pass filter, and only the modulating signal it will extract. That we will see. So when D of t is passed through the LPF, so I will write output of LPF. Let us consider this is Y of t. So y of t is equals to m of t divided by t. So this is my output of this synchronous detector, which is the modulating signal. Amplitude is reduced by half. Later on we can increase the amplitude with the help of audio amplifier. Okay. So this is my detection with respect to the mathematical analysis in time domain. Now we need to analyze this one in terms of frequency domain. Okay. So in frequency domain, what I will do, frequency spectrum. Okay. Now in frequency spectrum, what I will do, I will take d of t first, because that is the output of the mixer at a receiver end, in which we have two components. One is m of t by 2 and one is m of t cos 2 omega ct. So this is my resultant value divided by 2, like this I can write. Now I need to transform this whole value into the frequency domain. So frequency domain, I will write d of f. That means Fourier transform I have done. D of t to d of f. M of t will become m of f, amplitude is half. Okay. Now here this half whole into m of t and cos omega ct is available. So what will happen? Here we will get m of 2fc minus fm plus m of 2fc plus fm. So these are the components available and it is divided by 2. So it will become as a 4. Okay. So it is 1 by 4 m of 2fc minus fm, 2fc plus fm. Now these are the higher frequency component. It will be suppressed by the low pass filter. Our low pass filter is only tuned to the modulating frequency, or you can say the low pass filter frequency is central to the modulating frequency, so that it will extract only this much part. How? Let's see. So if I will draw the spectrum, let us consider this is d of f. We need to represent this value, d of f. So first, this is 2fc and this is minus 2fc. Okay, and this is this side which is called 2fc plus fm, and this is called 2fc minus fm. Here I have represented in semicircle. You can represent in spectral component also, no problem. It is same thing. Okay. So this is the upper segment and this is the lower segment. Similarly, the reflection part also I can represent 2fc plus fm, and here it is minus 2fc minus fm. Okay. So this is the upper segment, this is the lower segment. Here I write USB, here I will write LSB. Similarly, this is your LSB and this is your USB for second harmonic frequency, which is the higher frequency. Okay. Now another component is available, that is m of f, which is this. Okay, that is fm and minus fm. Okay. Now what is the amplitude available in these two segments? The amplitude is 1 by 4. So here I will write 1 by 4. Okay. And here I will write it is half of m of 0, because at 0 position the net amplitude is half. Now here what happens? This whole component is passed through the low pass filter. Okay. Now the low pass filter what will do? He will only identify the modulating frequency and suppress the higher frequency component. Now in this spectrum, which are the two higher component? This is the higher component and this is the reflection component. So it is centered to the modulating frequency, means my low pass filter only allow this particular part. So here I will write it is low pass filter. So output of the low pass filter is only the modulating signal suppressing this higher component. So here it is satisfied that output of low pass filter. Here I will draw the frequency spectrum of Y of f. Y of f means it is output of low pass filter, which is nothing but a modulating signal Fm minus Fm, and amplitude is half m of 0. So this is my output for synchronous detection. Done. So this is D of f, we have converted this D of f. Now this D of f is passed to that low pass filter. Low pass filter will only identify, or it is centered to the modulating frequency suppressing the higher frequency component. Now in this, what are the higher frequency component? This is the higher frequency component because this is second harmonic frequency. If there is a first harmonic also, it will suppress because carrier frequency is greater than your modulating frequency. So it will suppress this component. And then it will only allow the modulating signal at the output. So this is the output of a low pass filter. So here we are getting the modulating signal. So this is the basic concept behind the synchronous detection for DSB-SC signal. Okay. Now next we will discuss the squaring loop detector in order to demodulate the DSB-SC signal. So these relations are available in books. Some of the books in elaborate manner these relations are available, but in some of the books these relations are not available. So it's better to go through these videos and make a note of it. I will provide the notes no matter, but till then you need to maintain some hand notes with you so that when I will provide the notes you can correlate and make your own notes. Okay. So now we will discuss the squaring loop detector. It is also simple one. So what is the basic block diagram of the squaring loop detector? The basic block diagram is the received signal is fed to the squaring unit directly. No requirement of any carrier frequency. That is the advantage of the squaring loop. Okay. Then this, after squaring loop, it will pass through the low pass filter, and we should get some output, which should be modulating signal. Now here we have received the DSB-SC signal. Okay. Now this thing already we have discussed to demodulate the AM signal. The same thing I will discuss for the demodulation of DSB-SC signal. Same thing we can use for demodulation of SSB-SC signal also, using coherent as well as squaring loop detector. So first, the output of transmitter means the DSB-SC signal. So what is the DSB-SC signal? So DSB-SC signal is C of T into M of T, where C of T directly I can write cos omega Ct. So the transmitted signal DSB-SC of T is equals to M of T into cos omega CT. So this is the DSB-SC signal generated. Done. Now at receiver and what happens? At receiver, these all are mathematical analysis. Okay. So at receiver, the mathematical analysis is done. This received signal is fed to the squaring unit. That means if I am providing S of t to it, the output will become S square of t. Okay. So here I will write the output of squaring unit. Output of squaring unit. Let us consider this is d of t. So d of t is equal to S square of t. Now S square of t means we need to simply square this component. So what I will do? M of t into cos omega ct whole square. Okay. Expand. We will get m square of t, then 1 plus cos 2 omega ct whole divided by 2. Done. Now if you expand this, m square of t by 2 plus m square of t and cos 2 omega ct divided by 2. Okay. Now since this is the higher frequency component, and what is our m of t? M of t is Vm square cos square omega mt divided by 2. Similarly, Vm square cos square omega mt cos 2 omega ct divided by 2. Okay. See, here I have substituted what is the value of m of t. So that is Vm cos omega mt. Here you can consider m of t is equals to Vm cos omega mt. Then now if you expand this, you will get Vm square by 2. One is cos 2 omega mt. Here again it will expand, two segments it will come. So the output of LPF need to be centered at FM. So if it is need to be centered at FM, the output is available only with respect to this m square of t by 2. So here I can say the output of LPF. Okay, output of LPF. It is only centered to the modulating frequency. The modulating frequency component amplitude is increased, but frequency remain as it is. If it is squared, the frequency component will become as a second harmonic component, but still we have some sort of amplitude with it, and depends upon that we will get the output of LPF is m square of t divided by 2. So only this component, this higher component is going to be suppressed due to the presence of this carrier frequency. So this is the small explanation for the squaring loop detector. Okay. Now we will discuss about the envelope detection. Now remember this, in any of the detector, okay, either if it is synchronous detector, there we are multiplying the carrier. In synchronous detector, at a receiver section, we are multiplying the carrier. Means m of t cos omega ct, which is again multiplied with cos omega ct. We are getting m of t cos square omega ct. But in envelope detection, we are adding the carrier component to it. In synchronous detection, if it is synchronized, we can extract the data or extract the modulating signal. But if there is a phase discrepancy is there, that phase will hamper to my received signal. That we have seen while we are discussing about the AM detection. We have seen that phase, if phase is 0 degree, what happens? Phase is 90 degree, what happens? Phase is 180 degree, what happens? 270 is water pens and 360 water pens. So depend upon that we have identified those values. Okay. Now we will discuss about the envelope detection. Envelope detection. Envelope detection. In envelope detection, at receiver end, after receiving the modulated signal, a carrier component is added to it with some sort of phase discrepancy. Because envelope detection basically used for practical cases. But synchronous detection is very difficult to design, so we are not using that synchronous detector for practical usage. It is only for theoretical discussion is okay. Similarly, squaring loop is also for theoretical discussion, but for practical case, this envelope detection is going to be used. Okay. So I will write output of transmitter. So what is the output of transmitter? The output of transmitter is the DSB-SC signal. So first, this is the mixer product modulator, and then we are generating the DSB-SC signal. So here M of T is provider, product modulator, okay, product modulator, or here you can say the balance modulator also, product modulator, in which carrier is provided, that is cos omega ct, and DSB-SC signal M of T cos omega ct is generated and transmitted. Okay. So here I will write S of T, which is the DSB-SC signal, is equals to M of T cos omega ct. Only the sideband is available. If you expand this, then we will get half of, this is Vm by 2 cos of omega c minus omega m of t and cos of omega c plus omega m of t. So only the sidebands are available. This is lower sideband and this is upper sideband. Okay, so this is transmitted. Only sidebands are transmitted, suppressing the carrier. Now at receiver end, what happens? Receiver end. So in receiver end, what happens? We are receiving this DSB-SC signal, adding the carrier component to it, identifying the envelope, and from the envelope we are extracting the resultant output. Okay. So for DSB-SC signal, received signal is S of T, which is M of T cos omega ct. So this is the received signal. Now to this received signal, we are going to add C dash of T AC cos omega ct plus phi. Some phase discrepancy we are going to add to it. Okay. Now, so this is the carrier at receiver end. Okay, at receiver end. Now, this carrier is need to be, here we are receiving the signal, that is a product modulator passing through again LPM. This is the basic block diagram. Here there is a carrier. This is cos omega ct plus phi and AC, and this is the DSB-SC signal. Then this product modulator in envelope detection, what happens? We are adding the two components. This is the logic. But in other case, synchronous detection, we are multiplying the components. So here I will add these two components. So output, let us consider here it is y of t. Now y of t is equals to S of t plus C dash of t. Now S of t is m of t cos omega ct, that is the double sided suppressed carrier, and AC is AC cos omega ct plus phi. Okay. Now you need to expand this cos A plus B. If you are expanding cos A plus B, you will get cos A cos B minus sin A sin B. So here I will write m of t cos omega ct plus AC cos omega ct dot cos phi minus AC sin omega ct into sin phi. So this is the expansion. Now we need to identify the magnitude part available in this signal. So what I will do, I will take the common part one side. So you can see cos omega ct is available. So it is m of t plus AC cos phi into cos omega ct. So this is the first term. Now second term is minus AC sin phi sin omega ct. Okay. Now if you are taking, now I need to identify the magnitude of this, so that from that magnitude the envelope will be created, and from that envelope I can extract the method component from it. Okay. Now in that envelope you need to write, so this y of t is equals to E of t into cos of omega ct plus theta of t. E of t is the magnitude available in this component. Okay, and theta of t is the angle formed between these two components. That means now this is the y of t. Okay. Now from this E of t we need to extract the message signal, that is called envelope detection. This is the envelope of this particular signal, which consists of modulating signal, and your low pass filter will extract the modulating signal from the envelope available in the received in the derived sequence. Okay. Now here theta of t I will write, it is a tan inverse. You can see this is the y component and this is the x component. So it is a tan inverse of AC sin phi divided by m of t plus AC cos phi. So this is the angle of these two components. Now if you take the magnitude of this, the square component of this plus square component of this, it will come. That is called as the envelope. Okay, that we will discuss step by step. Okay, so what I will write E of t as I have written E theta. Theta of t is the angle available in this component. So E of t is equal to root over of AC plus m of t whole square, this is whole square, minus 2 suffix AC m of t whole into 1 minus cos phi. So this is the expansion of this particular magnitude. So magnitude available in this equation is AC plus m of t whole square, 2 AC m of t 1 minus cos phi. So sin square phi is converted into cos square phi. Next, so this is our theta, this is our E of t. Now from this E of t, I will extract the modulating signal, because this E of t, you can see here we have m of t. So I need to extract that m of t from the envelope with the help of low pass filter. Then we will say it is called as envelope detection. Okay, so these are the two components available in the output of your product module. Now here I can write y of t is equal to E of t into cos omega ct plus theta of t. The same equation I have written here. Okay. Now here cases arises. If your phi is 0, means if there is no phase difference with respect to the transmitted carrier frequency or with respect to the received at the receiver end whatever the carrier is available. If there is no phase change, this phi will become 0, this will become 0, so tan inverse of 0 is 0. So here I can say theta of t is equal to 0. How it is 0? As you can see, sin phi. So sin of 0 means 0. 0 by something is 0. Tan inverse of 0 is also 0 degree. So theta of t is this one. So my y of t, we have e of t and cos omega t. Over. Done. Now I need to calculate what is e of t. So what is e of t? E of t, in this you can see there is a cos phi term. If phi is 0, 1 minus 1 is 0. 0 is multiplied with 2 ACM of t, that is also 0. We will get AC plus m of t. AC plus m of t. So here you can see AC plus m of t cos omega ct. Now this equation is which sort of equation? This equation is an AM equation. AM equation. Done. Now with the help of this AM equation, we can extract easily the modulating signal. Done. Now next case, if phi is not equals to 0, then what happens? If phi is not equals to 0, means these are the static or standard equation to analyze or to extract the modulating signal. So this is for phi is equals to 0 degree, means this whole equation will become as an AM component. Okay. Now few equations are left. I will write those equations and we will wind up. So E of t if phi is not equal to 0. This is equal to 0 first case. If phi is not equal to 0, my E of t, if I will take AC component common outside, so I will get 1 plus 2 m of t divided by a cos phi plus m of t divided by a whole square to the power half. Okay. Now if a is very greater than m of t, means amplitude of the carrier is very greater than m of t. Now in this equation, if carrier amplitude is very greater than m of t, we can neglect this term, because anyway if a is very greater than m of t, the resultant will become negligible. So we can suppress this component. So what is left? 1 plus 2 m of t by a cos phi. So again, if a is very greater than m of t, then what will happen? So our envelope will become E of t is equals to AC plus m of t cos phi. So this is the envelope available if phi is not equal to 0 and your amplitude of the carrier is very greater than with respect to the modulating signal. If it is very greater than modulating signal, here you can see AC plus m of t and cos phi will be the resultant. This component will become as a negligible component, because A is anyhow it is very greater than m of t, you can suppress, we can neglect it. Second component is 1 plus 2 m of t cos divided by A. You take this AC inside, you will get AC, and here this A will be cancelled out, m of t into cos phi. So that is my envelope. Okay, and this envelope, with the help of this envelope, we can extract the modulating signal. Now this envelope, when it is passed through that low pass filter, for example, this is my low pass filter. Okay. Now E of t is provided here. This E of t is provided here. It will suppress the presence of DC component. AC is the DC component, and the resultant output will become m of t cos phi. So this is the modulating signal with phase difference. Now here you can check for phi is equals to 0 degree, phi is equals to 90 degree, phi is equals to 180 degree, phi is equals to 270 degree, and phi is equals to 360 degree. In this particular angle, you can put and check whether my modulating signal is available or not. For phi is equals to 0, your modulating signal will be in a positive polarity. If it is 90, 0. If it is 180, minus m of t you will get. Again, if it is 270, 0. If it is 360, again it is m of t we will receive. So this is the logic behind your envelope detection to extract the modulating signal. Okay. So this is about the DSB-SC demodulation. Now we will discuss about how we can transmit two DSB-SC signal without changing the carrier frequency. There is a modulation technique is available. Two DSB-SC signal with same carrier frequency to be transmitted through a particular channel, and which can also be recovered at the receiver end. Now remember that if there are two DSB-SC signal means if carrier component is same, that means your modulating signals are going to be different. So that modulation technique is called as quadrature amplitude modulation. That is QAM. It is called quadrature amplitude modulation. QAM, quadrature amplitude modulation. Now why it is called as quadrature? It is an amplitude modulation because it will generate two DSB-SC signal, which is a part of AM signal. But why it is called quadrature? The reason is when we are combining two DSB-SC signal, we are using only one carrier frequency. In order to provide two DSB-SC signal with two different components, we use a phase shifter which is 90 degree phase shifter. One modulated signal will be in phase and one modulated signal will be out of phase by 90 degree phase shift. Okay. So for that 90 degree phase shift, it is called as a quadrature modulation. So first I will discuss the transmitter part, and then we will discuss about receiver part. This is the receiver part. Then, so first transmitter part. So there are two modulating signals, M1 of T provided to this first product modulator PM1. Okay. To this product modulator, we provide the local oscillator carrier frequency as cos omega c. Now the same carrier is provided to the pi by 2 phase shifter. Means if I will provide cos to this, it will become as a sine. And in which second product modulator is available, in which I am transmitting another modulating signal. And this modulated wave we are going to add with the help of summer. And this suffix QAM. This is one modulated signal and this is the second modulated signal. But what is that modulated signal? This is the first DSB-SC signal, double sideband suppressed carrier, and this is also second double sideband suppressed carrier. How? Because M1 of t into cos omega ct, here you will get M1 of t cos omega ct. So this is the first double sideband suppressed carrier. Similarly, what is the difference in this? In this particular whole system, what happens? We are transmitting two modulating signal using the DSB-SC concept in a single channel using the certain bandwidth. Okay. So here first modulated signal is M1 of t cos omega ct, and the second one is M2 of t sin omega ct. Why it is sin? Because cos signal is passed through a phase shifter in which cosine signal is converted to the sinusoid signal, and the angle difference between cos and the sine is 90 degrees, so it is called quadratic amplitude modulation. Okay, and here what happens? Here we are adding these two sideband and transmitting to a particular channel. So this is called as your QAM signal. Okay. Next, at the receiver end, what happens? Again, we need to synchronize the same carrier frequency, so we will use the synchronous detection method. So this is the generation part of a QAM transmitter. Similarly, at receiver, we are receiving the QAM signal and we are providing to the mixer 1 followed by the low pass filter, and we will receive some output. Okay. To this mixer, cos omega ct is provided, and to another one it is phase shifter, and here the product modulator, or you can say the second mixer M2 is available. It is mixer 2. So the resultant output is followed by an LPF, and then we can extract the data. 1 minute. Now here we are receiving SQAM of, that means it consists of two DSB-SC signals. Same DSB-SC signal is provided to the first part as well as to the lower part. Then to that particular signal we will synchronize the carrier frequency. First, if I will multiply cos omega ct to the first QM signal, that means it will synchronize to this particular modulated signal because cos term is there. Okay, so it will become as a cos square, and cos square you can elaborate as 1 plus cos 2 omega ct. So cos 2 omega ct is a higher component. So output of this LPF we will get half of M1 of t. Done. Then same QM is provided to the second mixer in which sine component is available. So when sine component is multiplied with this QAM, it will synchronize to this component. So it will become as a sine square. And another component it will become as a cos and sine, which will become as a cos 2 omega harmonic component, and sine square will become as a 1 minus cos 2 omega ct, which is the harmonic. So output of this we will get half of M2 of t. So this is the basic block diagram of your quadrature amplitude modulation. So what is the advantage of QAM? The advantage of QAM, at a time two DSB-SC signals signals are transmitted without changing the carrier frequency. Our carrier frequency is how much? Omega c. But what we are doing? We are changing the phase of a particular carrier signal. In phase component is one DSB-SC signal, 90-degree phase shift another DSB-SC signal we are transmitting. That is the concept of quadrature amplitude modulation. Similarly, at receiver end, the demodulation takes place. The first mixer in which cosine signal is provided, it will synchronize to this particular signal where cosine term is available. Similarly, the second mixer in which we are providing the sine term, it will synchronize to the second message component, so that after demodulation we will get half m of t and this is half m1 of t. So this is the basic block diagram for QAM transmitter and QAM receiver. One task I will give. You need to write all these expressions from transmitter and mathematical representation, for receiver and mathematical representation in time domain, as well as make it in a frequency domain, represent in a frequency spectrum. That will be your task for this particular topic. Okay, so next class we will discuss about SSB-SC generation and detection. Thank you all.